Okay, we will go ahead and get started. So welcome to our first in-person lecture. This is the weirdest element of our lecture is this first minute or so, because we now have people on Twitch, which are up there, and the people in the room can see me pointing at the camera to the people on Twitch, which shows up over there on a slight delay. So it's all a little bit weird right now, but we're generally going to treat this like a normal class. So after the initial awkwardness of me explaining how this works, we'll pretty much just go back to the same way that the class has been previous to this. So we'll just keep on moving. What we're going to look at for the next probably 2 weeks or so is a molecular dynamics simulation that we had briefly introduced at the end of Friday's class. Today we're going to set up sort of the core of that. We'll do a little bit of math and then actually do the first few steps of the simulation. And then over the next week or two, we will just refine our simulation. We'll add new features to it. We will see different ways to do the same thing so that you can kind of learn what you prefer best, because like in so much coding, it's really up to you. There's often 3 or 4 or 5 different ways to do the same thing. So we're going to see a couple of different ways to do the same thing. Just as a heads up too for the midterm, the plan is it'll probably go out next Monday, and you'll have until the following Monday to do it. You'll be able to work in teams on the midterm, and it will cover, we've already gone through everything that you would need on the midterm. We're going to continue refining those ideas this week. And then of course the homework that's currently out, that was just posted like an hour ago, also covers the same ideas. So probably Monday to Monday, like next Monday to the following Monday, is what we're looking at for the midterm. Okay, so let me review a little bit just where we had picked up last time. And I got to make sure that this switches over because it failed last time. Yeah, let me change that really quick. Yeah, go ahead.
Would we be able to go to TA office hours during those final midterm?
Sure.
Yep.
All right, so evidently we cannot get Edge on here. Give me just a second to get the Edge browser up if we can see it. Nope, we can't see it. Oh, yep. Ta-da. Perfect. I don't know why it does that, but it does that. There. Now we are switched over. So this was a paper that I had pulled up last time, and we had briefly mentioned within this molecular dynamics simulation paper, A, there's a bunch of stuff we don't need, but B, there was this really nice summary. They were doing protein folding at the time, so they had modeled all of their atoms as hard spheres, which is the usual for a molecular dynamics simulation. And the structure that they had brought up for their code, the idea was that the basic molecular dynamics algorithm is what you're seeing here. The output of it is what we call a trajectory. So it's the paths of molecules through time. That's going to look not unlike our trajectory from the random walk simulation, except in the random walk simulation, we didn't really think about time, right? We just had, okay, take another step, take another step. But if you assign a time to those steps, suddenly you've got a trajectory. It's the same thing. If you just say 1 step per second, that's a trajectory. It's the same idea. The other thing that I had mentioned was the hardest parts of a molecular dynamics simulation in terms of what's hard for the computer to do are these force field calculations, the ones up at the top. So generating a potential energy field and then taking its derivative to figure out what the forces are. Usually we do that step analytically on paper and then just code the result. But even if you want to code the result, doing those force calculations in the code is A, computationally intensive, and B, it takes a fair amount of coding just to get the forces the way that we want them to do, or want them to be. So we will probably never deal with forces on this particular simulation. We'll find other ways to simulate that kind of behavior. So if there are no forces, that means there's no acceleration. And if there's no acceleration, that means velocities are constant. And that is typical of an ideal gas simulation, because ideal gases are point particles that don't interact with anything, right? They just fly in straight lines. They can't collide with anything because they have no size. And that's about the equivalent of particles that don't feel forces. And so that's going to be what we end up doing. So we won't do the energy calculation or the forces, but we will do this numerical integration. The numerical integration is also something that you'll practice on the first two homework problems. In the first two homework problems, it's like actual numerical integration, like if I needed to evaluate an integral. Here, our numerical integration is going to look like solving Newton's laws at little time steps as we go forward. So we're going to briefly derive these formulas. But in this class, I don't really care about the math so much. It's my intention to always give you the math and then have you code the math inside of Matlab. So we're doing this just to show you it's not pulled out of thin air, but it's not, don't think that I'm going to ask you to do this kind of math like on a midterm or on a homework or something like that. So let's switch over there really quick. And we're just going to do a little bit of note-taking to start. So let me zoom in here. We'll switch over here and talk about the basics of molecular dynamics, which is what we just saw right there. The basics of molecular dynamics, like I said before, come to Newton's laws, right? That's where they start. So from your physics class, you probably remember something like conservation of momentum in one form or another. Like you probably all had it in different forms. The form that we usually start off with is a differential form where the momentum of a particle with respect to time, the rate of change of momentum with respect to time, is equal to the sum of the forces on that particle. So this is Newton's, I think, second law? Something like that. I always get them confused. It doesn't really matter. It's conservation of momentum. But as I had said a moment ago, we're not going to worry about forces because ideal gases usually don't. So this ends up being equal to 0. The step that I don't really care whether you remember it or not, because I will always end up doing the math, is that if the momentum is defined as the mass times the velocity of a particle, and the mass is constant, then that comes out of the differential. And you may not have gotten to differential equations in your calculus class yet, but the end result of doing something like that is that the time rate of change of velocity is also going to be 0. You put in the m times the v, and the m pops out and gets divided by 0, or 0 gets divided by that. The result of this, whenever a time rate of change is 0, is that velocity, or generally that term, is constant. So the velocities of our particle, once they're given a particular velocity, they will keep that velocity for the entire simulation. They can't change it. There's no way to change it. And then the position comes from a definition of velocity, which the definition of velocity is the time rate of change of position. So this is equal to v sub I. And then if you were to integrate that, you get the working equation, the one that we're going to use a lot in our simulations, is that x, what we call x sub I in the notation that we just saw in the paper a minute ago, is equal to x of I minus 1 plus vi times what I'm going to call delta t. So however much time elapsed times the rate at which you are moving plus your old position is your new position. This should look similar to our random walk because what this is saying is the new position is equal to the old position plus a change term. The difference is that when we did our random walk, we didn't care what that change was, right? We just said plus 1 or minus 1 or 0. Now our change term is meaningful. It's the product of how long did you wait for the simulation to run between those two steps and what was the velocity of your particle. The way that we're going to write this, because we've written it this way before, is that x new is equal to x old plus a velocity times time difference. So we're going to call this velocity u. I'm going to change the symbols here really quick. because we also need one for the y direction. So y new is going to be y old plus v times delta t. There are different ways to distinguish the two velocities. So here I'm saying u is the x component of velocity and v is the y component of velocity. Sometimes people will call them like ux and uy or vx and vy or just a single vector, and then they'll deal with the components of that vector. Oops. It's not really important. It's just we have to pick some nomenclature and then be consistent with that nomenclature as we go. So that's the key idea, or I should say the key equations, which is conservation of momentum. The way that we're going to go about visualizing this is that if a particle starts at any point, let's say this is the old position, we're going to have a step in time, which then gets translated to a step in space. So if that is its initial position and this is its velocity, that velocity has two components, right? One of those components is u, because that's going in the x direction, and one of those components is v, which is going in the y direction, and then its final position will be out here. So its new position is here. And then we just keep updating that over and over and over and over and over again, and that becomes our simulation. We're not going to try to animate this just yet, so maybe towards the end of next week, we will look at how we can animate things in Matlab and make them sort of play like a movie. But usually animation is fairly computationally intensive because it has to wipe drawings and then redraw them. That gets hard to do. It's part of the optimization they have to play in video games where they don't want the math to be too expensive because so much of the processor time is just drawing what's on the screen. That takes a little bit. So the trajectories that we're going to be drawing will look more like the particle was here, and then the particle was here, and then the particle was here, and then the particle was here. And we'll see all of those spots all at once, right? Our sort of product that we want would be something that looks like this. And we're going to bend that stem convention for now and actually draw all of both the line and the dot, because we learn a little bit from both of those. A, we recognize it's a line, and B, the dot tells us how often we were making our simulation, and that can help us troubleshoot our simulation. So that's what we're after, a simulation that doesn't, at least conceptually, have too much of a difference from what it was before, but the differences are in the details, right? It's still taking an old value, adding a change, and making that a new value. That part is going to stay the same. Other things that'll change are what do we do when the value reaches a certain value, or when the position reaches a certain value. That we'll get to either at the very end of today or in tomorrow's lecture. So let's look at some pseudocode for molecular dynamics. And just as a heads up too, going forward, at least for the next 2 weeks, the lectures are going to be more interactive in the sense that more often I will just set up a small part of the code, and then we will wait for like 10 minutes or something while you code more portions of it. Obviously, I'll be here for any questions that you have, but also just for anybody watching on Twitch, try to play along if you can. Or if you're watching the video, try to pause it when I pause it here, because I think you'll get more benefit of actually trying the code than just skipping to the answer of what I was doing. So that's going to happen a lot over the next couple of weeks as we do this kind of stuff. All right, most molecular dynamics simulations, in fact, most approaches that we have to problem solving get split into 3 chunks. The first is initialization. And when you get into the initialization phase, you're setting constants, right? You're setting up, how do I want the simulation to behave once it starts? So this could be things like setting x0 and y0, setting the velocity in both of the directions, setting the time step, which I'm going to call dt instead of delta t, that sort of stuff. All right, you just define all of your constants. Pre-allocation is also a good idea. So we're going to pre-allocate vectors for x and y, and that, just like we saw with the random walk simulation, those will be the things that hold our trajectories, right? Each location in there will be the position of a particle at a new time. And then I'll just say et cetera, because I usually forget something until I start coding, and then I add it afterwards. Then you start the simulation itself, which is an iteration. And the kind of iteration that we want to do is for each time step. So there'll be some kind of an end that goes in here. What do we want to do each time? We want to update the position. So we want to set the new is equal to the old plus the velocity times the time change. And we have to do that for the x position and for the y position. And there's various ways that we can do that. And we've actually seen a couple of them, but we will see more of them as we go. And then we have to store these positions in x and y. That's the basic step of our simulation, is calculate the new positions based on the old positions and then store those in our vectors x and y. One thing that we're going to have to do in the future, which we're not going to do or probably have time to do today, is in between the storage and the calculation, we have to check for collisions. So I'm going to put that one in parentheses because we probably aren't going to do that today. But we will, if we do, it'll be at the end of today, or we'll start with that step on Wednesday's class. And then the last part is analysis, or sometimes it's called post-processing. And here, what we're going to do is plot the trajectories. So that's going to give us a plot that looks like what we just saw a moment ago, where we've got little dots on a grid or something like that. But there could be all sorts of different things that you might have to do with post-processing. This sort of a setup of initialization and then calculation and then post-processing, it's illustrated here from molecular dynamics, but really it's for any problem that we end up solving in a computer. We set it up, we solve it, and then we probably analyze something afterwards. So I'm not picking on molecular dynamics for this particular setup. It's really the other way around. This setup happens to be used in molecular dynamics because we just kind of do that in most of them, right? Code operates from top to bottom, so it tends to be set it up, solve it, and then analyze it. It's just the way a problem gets solved. So before we switch over to, that's as far as the pseudocode I'm going to go. Before we switch over to Matlab, are there any questions on why we're doing anything in there? Because the next thing that I'm going to do is set up parts of this in Matlab and then turn you loose for about 10 minutes or 15 minutes to try to code as much of this as you can. So far, so good? Okay, we'll switch over to Matlab. I'm going to continue to use scripts. So I said in homework 2, we were using a lot of live scripts. But when we're doing these sorts of simulations, time is a little bit more important because the calculations tend to take a little bit longer. So we're just using plain scripts. So to give yourself a new plain script, it's still new script up here. I'll just delete this, and I'm going to save it so we don't lose it. Lecture 12B. And I'm going to first add those 3 areas, right? There's going to be an initialization step, there's a simulation step, and then there's an analysis step, or analysis, post-processing, whatever you want to call it. Right, so this is our iteration, and then we have to initialize the values first. So what kind of things do we have to initialize? Well, it is going to be a particle. We're going to restrain our particle to be inside of a box. So it's going to, the box length is going to be 1 unit long on every side, and the bottom left will be at 0, 0, and the top left will be at 1, 1. So it'll be a nice little 1 by 1 by 1 square. So we have to pick an initial position that's somewhere in that square. I'm just going to start it at the center. So I'm going to say x0 is 0.5 and y0 is 0.5. So this is our initial y position, and this is our initial x position. I'm going to start the time step fairly small, and we'll talk about what the different step sizes mean in a little bit. But then we would also have to initialize things like u, v, x, y, and the number of steps. Once we've got those initialized, then we have to come down here to our simulation, and that's going to look something like, for each step, something, something, something with an end at the end. And somewhere inside of that step, or somewhere inside of that simulation, there's got to be something that looks like x new is equal to x old plus u times dt. And similarly, a y new is equal to y old plus v times dt. So remember, these are Newton's laws, which I, again, think is Newton's second, but I honestly never remembered any of the numbers, so I don't really know. And then, of course, the other things that have to happen in that step is you have to define the old, define x old, define y old, and then after you calculate the new values, store them inside of those vectors x and y that you pre-allocated previously. And then the plot that we want to do is a trajectory. So we're going to say plot x comma y, and we're going to make it a blue dotted line. And like I said, we're bending the stem convention here of normally functions always get a line and data points always get dots. Here we're doing both because we can learn something from both of them in the simulation. Later we might switch to just lines, but right now having both the dots on there, dots and the lines are good. So I'm going to leave this up here, and we're just going to go until probably like 3:30, 3:35, something like that, and just see how much of this you can get through as we go. And then I'll come back and code up what I've got. But that process of practicing it first will be pretty helpful, I think, versus just watching me code it. So I'm going to shut up here, but I am over on Canvas chat for anybody watching on Twitch. If you've got any questions, you can throw them in there. But otherwise, I'll just go silent for a while everybody works. Okay, so let's tackle this, the various parts. First of all, we don't know what U and V are. I didn't define what U and V are, but we know what they need to be in terms of their shape. They should just be a constant, right? Because we said there's no forces between these things, so they're just going to be constants. I'm going to start off with fairly small values of about 0.2 and 0.3. So this is our y velocity, or kind of y velocity, y speed, if you want to call it that, and x velocity. I'm also going to pick them to be different, just so that I can see when the plot is done whether or not I'm using the velocities correctly. Because if the y velocity is bigger than the x, I expect it to move sort of up and to the right, but a little bit more up than it did to the right, because I made the v a little bit higher. And that's one of several sort of sanity checks that we're going to do when we're done here, that are nice when you're building up these simulations, because you can check sort of basic behavior before you complicate the problem even more. So we've got our u and our v. We've got our dt. We need a number of steps, which again, I'm going to start off as small, because if I can get it to work for about 10 steps, it should conceptually work for thousands of steps. It's not a question of 10 versus 20. It's kind of like what the physics folks say, like the only numbers that exist in physics are 1, 2, and many. Right? If you can do it for more than 2, you can do it for any number of things that come after that. So 10 is fine. And then we need to pre-allocate those positions. So I'm going to pre-allocate mine as column vectors, just because I'm used to sort of from Excel, right, seeing everything in a column rather than a row. So I will pre-allocate both of these. There's no reason either that these have to be separate. So another option could be a matrix of something that's like n steps and 2 columns. And so this would look like a column of x and a column of y. That would also be okay, right? If you prefer to keep everything bundled as a matrix, that's okay. I'm in the habit of using vectors. But pretty rapidly, we'll have to transition to matrices anyway. So there's those. If I just start off with the general definition, or the general outline of a for loop that we had introduced originally, this would look something like for I dx is equal to 1 to the number of steps. So let's start with that and then see what we have to do to change that for this particular simulation. Which, by the way, going forward after probably Wednesday, I'm going to stop calling this I dx and start calling it I, just because I'm lazy and typing the dx is a little bit more than I care to do. Let's say we wanted to keep it in this form, right? So we keep Newton's second law written out just the way that we did by hand. That means we would have to define the old x and the old y before we do that calculation. So we would say something like x old is equal to x of I dx minus 1. The reason that we do that is because that is the same approach that we did on the random walk simulations, where we say get the previous value by looking at whatever row we're at right now that we're indexing, but minus 1, right? Go 1 right before that. And so when I say I dx minus 1, what problem does that present with our for loop? If I were to leave the for loop the way that it is right now, there's a problem with I dx minus 1. Can anybody spot it? It would technically start at 0, right? Because we have a 1 here. That's the very first value of I dx. You can't index into the 0th element of a vector. Indexing in Matlab starts at 1, so this would have to start as 2. That also introduces another slightly subtle problem related to where the particle starts. Anybody catch the problem there? Less than 2?
Right, isn't it starting at 0.5?
Yes, exactly. And so when we were doing our random walk simulation, these 0 pre-allocations that we did here, those were fine, right? We could just go to the next row because 0, 0 was already where we wanted to start. But now we want to start at 0.5 and 0.5. So we have to add an extra step to say, yeah, I pre-allocated all of these to be zeros, but I also know the first one. So I need to put the first value in there. So I would say something like x of 1 is x0 and y of 1 is y0. So this sets the initial y, and this sets the initial x. I should say the initial x position and the initial y position. So then we do our calculation. Actually, I need to do the y's as well. So y old is y of idx minus 1. We do our math, and then we have to store those values. So the storing happens at idx, and that's going to be x new, and y of idx is going to be equal to y new. There's no reason that those have to be split apart, right? This x old only gets used right here. So there's no reason that we can't just combine those into one step. So if I were coding this up more, I guess, in the line that I would normally do it, I would have something along the lines of x of idx is x of idx minus 1 plus u times dt. Right? It's also okay to not split those up. I'm splitting them up here so that we can clearly see what's being indexed where and what the notation is. But this is actually closer to the way that we saw it on that paper. Right? The way that we saw it on the paper was x of I as x of I minus 1 plus u dt. That's what this is. It means the same thing. And then we've got our plot, which we don't have to change at all right now. A couple of things that can help you troubleshoot when you're setting these scripts up. First, I always look up here at the top right and look for that little green check, or you might have a green box. It sort of depends. Green is the best. It means you haven't made any obvious syntax errors. Orange isn't bad. Sometimes orange will just mean like Matlab thinks you can do something faster, but it's okay. Red means you've made a syntax error. So never hit the run button if that thing is red, because it's just going to fail. Go find the red line and it'll tell you. You're probably just like missing a parenthesis or something. So red, definitely don't run it. Green, that's sort of my indicator to say, go ahead and do it. Like, I haven't made any obvious syntax mistakes. It doesn't mean I haven't made any mistakes. But it's worth at this point at least starting to run the code and debug it as we run it. So I'm going to run this and we're going to look at what it gives us. I'm going to dock this so that everybody else can see it. So here's the plot that we have. So let's do some of those sanity checks, right? Because as you're building up more and more complicated behavior in your simulations, it's best to do some basic checking. First of all, do we know if the particle started where it was supposed to? Close. We know it was supposed to start at 0.5 and 0.5, and we know at least one of the two endpoints that we have here is at 0.5 and 0.5. So it seems reasonable that it probably started there and went in the other direction. It was supposed to travel in a straight line because that's the ideal gas, right? It doesn't have any forces acting on the particle. This sure looks like a straight line, so it's probably okay. Did it count all of the steps that we needed, right? We were supposed to go from 2 to n steps, which should be somewhere around 9 or 10. And if I count each one of those dots up, that's about 10. That's one of the reasons why we put the dots in there, is so that we can make sure we're going through the right number of steps. And then last, did it stay within the domain that we wanted? Yeah, it's less than 1 on all sides, but this is one place where we can help ourselves a little bit if we change the way the plot is displayed so that it only displays between 0 and 1. So we could add x limit is 0 to 1, and y limit is also 0 to 1. And just for making the plot look a little bit nicer, if we say axis square, this will give us a square aspect ratio. So it'll actually look like a square. It won't be, set by whatever our figure size is. There's another way to set aspect ratios, which is called PB aspect. So if you just Google MATLAB set aspect ratio or something like that, you might get one that's PB aspect, and you give it a vector of 3 values. And this gives you your x, your y, and your z aspect ratio. So I only bring that up because that's one of the first things that shows up if you ever Google MATLAB set plot aspect ratio. It works the same way. If you do PB aspect 111, you'll get the same thing as aspect square. So you can use either one. But if you needed it to be like twice as long as it was tall, you could do 211 or that sort of thing. So let's run that again and just take a look at our plot over there. And seems like a reasonable plot, right? It went off in one direction. We should do a couple of more checks too, just to make sure. If I wanted to move the starting position to the bottom left, what would you do? What would I change in the code to move the starting position to the bottom left? You could transpose it, but that's messing with the whole thing. What I want to do is just move the starting position and then let it calculate the new positions as it goes. So I would have to change two values. Which two values would I have to change? Which two say this is where I start? Yeah, the initial what?
Positions.
Yep. So the x0 and the y0, if I've coded this correctly, what those mean is that's where the first dot goes. So one of the sanity checks that you can do is to mess with the initial conditions and see if the plot behaves the way that you think it will. Better to check that stuff now than when you've got like 30 particles on here and 30 trajectories. It's really hard to figure it out then. So if I wanted to move it, let's say, very close to the x-axis, but a little bit further away from the y, I could say x0 is maybe 0.05 and y0 is 0.2. And so I do a little thought experiment in my head to say that ought to be pretty close to the x-axis, but a little further away from the y. And so if I run that, okay, I didn't do it quite right? In my mind, I had it reversed. That actually meant that it was really close to the y-axis and a little bit further away from the x-axis. But now that I do that, it's helped clarify in my mind exactly what's being plotted on here. Should the velocity be able to be negative? Should be, right? That just means it's going in the other direction. So if I set, say, the x velocity to be negative and run it, I get something of a problem. It did behave the way that I expected it to, right? It now sent the particle off to the left instead of off to the right. It went off of the screen, though. That doesn't mean that it failed. It just means we haven't implemented that particular behavior in our simulation yet. Another really good check that you can try every once in a while is send it perfectly horizontal and perfectly vertical. So for example, if I set this to be 0.4 and I set velocity in the y direction to be 0, I had better get a horizontal line on there. Right? These are all just sanity checks you can use to make sure that the variables make sense in your mind and they are affecting the plot in a way that you would normally expect them to. The negative thing is particularly helpful because if you've messed up your indexing somewhere and you put a negative value into your index, that will almost undoubtedly throw an error that wouldn't have been caught by the syntax checker. So throwing some negative signs in there can be helpful as well. The last thing that we're going to do, which I don't think we're actually going to get to the point of, we can probably sketch it and then we'll code it up next time, is to figure out what happens when we go off of the screen. So let's leave it going horizontal here and say that our time step gets a little bit bigger. Let's go up to 0.3. It went right off to the edge and then went beyond, right? This is actually highlighting one of the biggest drawbacks of a molecular dynamics simulation is how big can the time step be? In our case, the time steps can be pretty big. The only thing that will happen is it'll go off the side of the plot. In a real molecular dynamics simulation, those time steps have to be small enough that the atoms barely move. Because if they move too much, they can actually get to a state where they're overlapping between the previous step and this step. And now one molecule's on top of the other one. And if you calculate the forces there, they're going to blow up. I mean, close to literally, like the velocities will be absolutely enormous. And that's actually one of the drawbacks in games, right? One of the balancing acts you have to do in games is you want the physics to be accurate enough so that people believe that they're doing whatever it is that they're doing. But you also want those time steps to be as big as possible so you don't have to do very many calculations. That way you can reserve more time for drawing things to a screen. In a normal molecular dynamics simulation, this time step is usually on the order of something like 10 to the minus 12 to 10 to the minus 15 seconds. It's, picoseconds, femtoseconds, that sort of stuff, because those are the timescales on which atoms move only a little bit. We are not going to do 10 to the minus 12 or something like that because that means there are billions of calculations just to get 1 second worth of actual simulation time. So we're not too worried about that time change. But as the time change gets bigger, we can see the problem that we haven't accomplished or that we haven't solved yet is the thing goes off of the screen. So we're going to spend like the last 3 minutes just talking about how we would fix that. And then we'll start up there on Wednesday with coding that up. So in the current state, the simulation works. It's just we need that extra step. The extra step was to do the wall check. Let me switch back over to Excel and we'll talk about how we do a wall check. So let's say this is our wall. And we'll pretend first that we're going off to the right, and then later on we will cover each of those. What we're interested in doing is figuring out, let's say my initial step was here. This was old. And then I calculate the new position, and the new position is somewhere over here beyond the wall. Right? This is our new position here. What we need to do is say you can't go past the wall, right? The actual position ought to be somewhere back here, right? That's the real one. What that describes is, if you kind of stretch this out, it went over to the wall, bounced, and turned around to about wherever it is right there. I'm kind of dragging that out in the vertical direction, but that's the behavior that we need to simulate is I went over to the wall, I tried to go through it, but I can't actually go through it, so I need to apply a correction in order to go back to the other side. The way that we do that, we know this distance is fixed, right? This distance is always going to be u times dt. And we know that the amount by which we went over here has to be equal to the amount that we came back over here. So because that distance is fixed every time, we always have to travel the same amount of time. So what this is saying is, I know I've got this much just to get to the wall. I should, if the calculation didn't hit the wall, have gone that far off to the right, but I did hit the wall, so I need to go instead that far off to the left, so that the total distance traveled is still the same. So if we call that distance L, it's the same L on either one. The wall happens to be located at position 1 when we got started. The wall will always be over there at position 1 on the far outside of the wall. So we need to calculate what is this distance L. So the distance L is equal to whatever x new is, because that was the one that took us beyond the wall, minus 1. 1 being the location of the wall. If the wall were at 10, then it would be x new minus 10, wherever the wall position happens to be. And then what is this new one? We need to give a new position down here, like a corrected position, this one, x new. We're going to denote that as x new prime, which is our corrected one. So it's like x new, but it's after we've applied a wall condition. What's x new prime? X new prime will be whatever the distance is that the wall is located at, which is 1, minus this factor L. Right? Both of those distances have to be the same. I went L past the wall, that was wrong. I reflect it and go L in the opposite direction of the wall. And so I can substitute in a couple of these values and get my first wall correction, which is 1 minus L, and L is x new minus 1. And so the corrected value is x new prime is 2 minus x new. And so what this becomes is, this is the correction that we have to do if we've detected that we went past a wall. And that's the kind of detection that we're going to work on Wednesday, is setting that up. We can't use vector notation like we did for the random walk. We also can't use well, I suppose we could use a switch case, but it's a bad idea. Switch cases aren't designed to handle this. But there is that if statement that we briefly talked about, before, and that's very well suited to this, right? It just says, if you've gone beyond the wall, do that correction. And we'll have to generate those corrections for all 4 of the walls and both of the positions, right? The X and the Y. And they're all going to look something like this. So we will wrap it up here. I'm going to stick around, of course, a little bit here in person, of course. But if anybody on Twitch has other questions on chat as well, feel free to throw them up. Otherwise, I'll see everybody back here on Wednesday. Have a good one, everybody.